Hello and welcome to the session on elementary functions. Algebraic function of z is a function w is equal to f of z, which is a solution of the polynomial equation p naught of z w raised to n plus p1 of z w raised to n minus 1 plus etc. plus pn minus 1 of z w plus pn of z is equal to 0, where p naught of z is not equal to 0, p1 of z, p2 of z, etc. pn of z are polynomials in z and n is a positive integer. Polynomials and rational functions are special cases of algebraic functions. Transcendental functions are those which cannot be expressed as an algebraic function. Logarithmic, trigonometric, hyperbolic and their inverses are transcendental functions. Elementary functions consist of algebraic functions and transcendental functions and functions derived from them by a finite number of algebraic operations of addition, subtraction, multiplication and division and root taking. In other words, an elementary function is a function of one variable built from a finite number of exponentials, logarithms, constants and nth roots through composition and combinations using the four elementary operations addition, subtraction, multiplication and division. By allowing these functions and constants to be complex numbers, trigonometric functions and their inverses become included in the elementary functions. The roots of equations are the functions implicitly defined as solving a polynomial equation with constant coefficients. For polynomials of degree 4 and smaller, there are explicit formulae for the roots. The formulae are elementary functions. Elementary functions were introduced by Joseph Liouville in a series of papers from 1833 to 1841. An algebraic treatment of elementary functions was started by Joseph Fels-Rit in the 1930s. We consider here various elementary functions studied in calculus and define corresponding functions of a complex variable. To be specific, we define analytic functions of a complex variable z that reduce to the elementary functions in calculus when z is equal to x plus I into 0. We start by defining the complex exponential function and then use it to develop the others. The exponential function. The exponential function is the function e raised to x where e is the number approximately 2.718281828 such that the function e raised to x is its own derivative. The exponential function is used to model a relationship in which a constant change in the independent variable gives the same proportional change, that is percentage increase or decrease in the dependent variable. The function is often written as exponential of x, especially when it is impractical to write the independent variable as a superscript. The graph of y is equal to e raised to x is upward sloping and increases faster as x increases. The graph always lies above the x axis but can get arbitrarily close to it for negative x. Thus, the x axis is a horizontal asymptote. The slope of the tangent to the graph at each point is equal to its y coordinate at that point. The inverse function is the natural logarithm log x. Because of this, some old texts refer to the exponential function as the anti-logarithm. In general, the variable x can be any real or complex number. As in the real case, the exponential function can be defined on the complex plane in several equivalent forms. If a function f of the complex variable z is equal to x plus iy is to reduce to the familiar exponential function in calculus when z is real, we must require that f of x plus I into 0 is equal to e raised to x for all real numbers x. In as much as e raised to x whole bar is equal to e raised to x. That means derivative of e raised to x is equal to e raised to x for all real x. It is also natural to impose the following conditions. F is entire and f dash of z is equal to f of z for all z. We know that the function f of z is equal to e raised to x into cos y plus I sin y, where y is to be taken in radians, is differentiable everywhere in the complex plane, and f dash of z is equal to f of z. So, the required conditions are clearly satisfied by this function. That is, f of z is equal to e raised to z, which is equal to e raised to x plus iy, which is equal to e raised to x into cos y plus I sin y. For convenience, we use the notation exponential z instead of e raised to z. The exponential function of complex analysis is thus defined for all z by means of the equation e raised to z is equal to e raised to x into cos y plus I sin y, where z is equal to x plus iy. Let us consider this as equation star. Now, about the figure, exponential function on the complex plane. The transition from dark to light colors show that the magnitude of the exponential function is increasing to the right. The periodic horizontal bands indicate that the exponential function is periodic in the imaginary part of its argument. It reduces to the usual exponential function in calculus when y is equal to 0. It is entire and differentiable everywhere in the z plane. When z is the pure imaginary number I theta, expression star becomes e raised to I theta is equal to cos theta plus I sin theta, which is the Euler's formula. E raised to z is equal to e raised to x plus iy, which is equal to e raised to x into e raised to iy. This form can in turn be written as e raised to z is equal to rho e raised to I theta, where rho is equal to e raised to x and theta is equal to y. Consider this equation as 1. From equation 1, modulus of e raised to z is e raised to x and an argument of e raised to z is y. That is, the number rho is equal to e raised to x is always positive, since rho is equal to e raised to x is the modulus of the complex number e raised to z. Because of the same reason, e raised to z not equal to 0 for any complex number z. The additive property of exponential function, that is, e raised to z1 into e raised to z2 is equal to e raised to z1 plus z2. This can be verified by taking z1 is equal to x1 plus iy1 and z2 is equal to x2 plus iy2. z1 plus z2 is equal to x1 plus x2 plus I times y1 plus y2. E raised to z1 into e raised to z2 is equal to e raised to x1 plus iy1 into e raised to x2 plus iy2, which is equal to e raised to x1 plus x2 into e raised to I times y1 plus y2, which is equal to e raised to x1 plus x2 plus I times y1 plus y2, which is equal to e raised to z1 plus z2. Also, e raised to z1 divided by e raised to z2 is equal to e raised to z1 minus z2. We know that e raised to 0 is equal to 1 and 1 by e raised to z is equal to e raised to minus z. E raised to z1 divided by e raised to z2 is equal to e raised to z1 into e raised to minus z2, which is equal to e raised to z1 minus z2. Note that e raised to z is periodic with a pure imaginary period of 2 pi I. E raised to z plus 2 pi I is equal to e raised to z into e raised to 2 pi I, which is equal to e raised to z into 1, because e raised to 2 pi I is equal to cos 2 pi plus I sin 2 pi, which is equal to 1. That is, e raised to z plus 2 pi I is equal to e raised to z for all z. Next is an example to show that there are values of z such that e raised to z is negative. Example 1. There are values of z, for instance, such that e raised to z is equal to minus 1. E raised to z is equal to minus 1, which means that e raised to x into e raised to iy is equal to minus 1, which implies e raised to x into e raised to iy is equal to 1 into e raised to I pi, which implies e raised to x is equal to 1 and y is equal to pi plus 2n pi, where n is equal to 0 plus or minus 1 plus or minus 2 etc. Thus, x is equal to 0 and y is equal to pi plus 2n pi, where n is 0 plus or minus 1 plus or minus 2 etc. That is, z is equal to 2n plus 1 times pi I, where n varies from 0 plus or minus 1 plus or minus 2 etc. Now consider another example. Show that e raised to z satisfies Cauchy-Riemann equations. F of z is equal to e raised to z, which is equal to e raised to x into cos y plus I sin y. Here u is equal to e raised to x cos y and v is equal to e raised to x sin y. Thus, ux, that is partial derivative of u with respect to x, is equal to e raised to x cos y. Vx, which is the partial derivative of v with respect to x, which is e raised to x sin y. Uy means partial derivative of u with respect to y, which is equal to minus e raised to x sin y. Similarly, Vy, partial derivative of v with respect to y, is equal to e raised to x cos y. Now we can see that ux equal to Vy and uy equal to minus Ex, which is the Cauchy-Riemann equation. Now consider another example. Show that the derivative of e raised to z with respect to z is equal to e raised to z itself. We know that if f of z is equal to u plus iv, then f dash of z is equal to ux plus ivx. F of z is equal to e raised to z, which is equal to e raised to x into cos y plus I sin y. Here u is equal to e raised to x cos y and v is equal to e raised to x sin y. Now consider the partial derivative of u with respect to x, which is equal to e raised to x cos y. Also consider the partial derivative of v with respect to x, which is equal to e raised to x sin y. Thus, f dash of z is equal to ux plus ivx, which is equal to e raised to x cos y plus I e raised to x sin y. Taking e raised to x outside, which is equal to e raised to x into cos y plus I sin y, which is equal to e raised to z. Thus, d by dz of e raised to z is equal to e raised to z itself. Plots of the exponential function on the complex plane. The exponential function maps any line in the complex plane to a logarithmic spiral in the complex plane with the center at the origin. Two special cases might be noted. When the original line is parallel to the real axis, the resulting spiral never closes in on itself. When the original line is parallel to the imaginary axis, the resulting spiral is a circle of some radius. Let me summarize this section. From this section, a learner goes through one of the elementary functions called exponential function, which is a stepping stone to various other complex elementary functions. The various properties of the exponential function are discussed. The assignment section helps him to analyze how much he is thorough with the topic. Now you can try to solve the following problems. First question. State why the function 2z square minus 3 minus z e raised to z plus e raised to minus z is entire. Second question. Show that if e raised to z is real, then y is equal to the imaginary part of z is equal to n pi for n is equal to 0 plus or minus 1 plus or minus 2 etc. The third question. Establish the identity e raised to z whole raised to n is equal to e raised to nz. Fourth problem. Prove that modulus of e raised to minus 2z is less than 1 if and only if real part of z is greater than 0. Fifth problem, find all solutions of e raised to 2z minus 1 which is equal to 1. Prove that f of z equal to e raised to z is an entire function. You may refer the following books: Complex Variables and Applications, the 6th edition by James Ward Brown and Ruel V. Churchill, published by McGraw-Hill International Editions. Another one, Complex Variables, the Introduction and Applications by Mark J. Ablowitz and Athanasius S. Fokas, Cambridge Texts in Applied Mathematics. Also, Complex Variables by Herb Silverman, Houghton Mifflin Company, Boston. Also, you may refer the website www.mathworld.wolfram.com, also www.wikipedia.org. Hope that you have enjoyed this session. We can meet again with another topic. Thank you.